Okay, good morning to everyone and oh, my driver is not one moment. Let me know if my screen is visible.
Yes, sir, visible.
Okay. So yesterday we discussed about the first law for control volume and mass conservation, which is trivial. So now we will move on to steady state processes. Okay, so steady state processes, I mean this kind of assumption is true for a majority of devices such as turbines, compressors, nozzles, boilers, heat exchanger, and so on. So what is the common theme for all these devices which operate at steady state? That there is some mass flux coming in, it could be multiple sources, and there is some mass flux going out, and these mass fluxes are constant. Okay, the mass fluxes are constant, meaning they do not change over time. If they do not change over time, there will be no rate of change of mass in the control volume as well. Okay, if we say that something does not change in time, ddt of that quantity will be 0. So in that case, we will say that the system is operating in steady state. So imagine for a turbine, and we have seen this yesterday also. So there is some mass stream coming in, there is some extraction, there is something which is going out, and these mass fluxes do not change. For a turbine, it may change when, say, the power plant is shut down, for example. Okay, so there are host of devices, and so we will have certain assumptions also built in. You will see that in majority of the problems, the control volume does not move, mass inside control volume does not change, okay, and the mass fluxes coming in or going out of the control volume, it also does not change in time. When these are sort of valid, then we say that the process is in a steady state, steady flow process. Also it's also steady state, steady flow. SF is steady flow. So steady flow is this assumption, because the mass of the control volume can also not change when the inlet flux and the outlet flux change in time, so that the difference is 0. This can also happen. So to avoid that extra, you know, ambiguity, we will have the third assumption also coming in, that is steady flow. Okay, so let's do some examples. And as I said, the examples are really easy. I mean, the problems in all of this, they are very easy, but the only point is you must practice. So let's consider first the analysis of heat exchangers. Heat exchangers. And you will see heat exchangers everywhere in cars, air conditioners, refrigerators. You will see them on in power plants. You will in fact see something similar in personal computers. In fact, if you have liquid cooling, as I do, then you will see that the liquid cooling line is connected to a big heat exchanger. And Typically nowadays people buy those RGB, cooling fans. So inside the cooling, I mean behind the cooling fan is a heat exchanger. So let me show you how it actually looks like. Let me just paste an image. A heat exchanger looks something like this. So this is a kind of heat exchanger where hot liquid comes in, hot liquid goes out, rather hot comes in, cold goes out. And how is the hot liquid cooled? By means of cooling air which blows over these fins. You will study it in heat transfer, that when you blow air over these fins, the air takes up the heat from the hot liquid and becomes cold. But there can be different kinds of heat exchangers as well. This is what goes on in a PC, personal computer. You have the CPU water block, and so because of the heating of the CPU, the water inside the water block becomes hot. So the pump simply pumps the hot water to the radiator, where fan draws in air. So it draws cold air, and because the cold air will pick up heat from the hot water, the air will become hot, but the liquid will become cool. Okay, this is how it looks like. But here in both the examples we had air, but you can imagine that instead of air you could have cooling water as well. Okay, you could have, instead of air blowing over this, you could have cold water coming in and hot water going out. So let me draw a schematic of it. Okay, so you have cooling water in, and so cooling water will flow in this space, where the tube isn't. So this tube I have just shown schematically. It's like a coil. So cooling water will flow over the coil and it will exit. But hot refrigerant will come, it will go through the tube. So thus this kind of tubes in those old refrigerators you will see at the back. Okay, it will go in the tubes and it will exit. So what will happen? The cooling water will pick up heat from the hot refrigerant, and so the cooling water will become hot, but the hot refrigerant will become cold. It is as simple as that. So let's do a problem. Once we do the problem, it will be immediately clear. Okay, internally you have those tubings going on so that the two liquids do not mix. So in the problem, it is given that we have a water cooled condenser, in which R134A is the refrigerant, and the refrigerant enters the condenser at 1 megapascal, 60 degrees Celsius, at a rate of 0.2 kg per second, and exits the condenser as liquid at 0.95 megapascal, 35 degrees Celsius. The cooling water enters the condenser at 10 degrees Celsius and it exits the condenser at 20 degrees Celsius. This is water, and this is R134A. So we must determine the rate at which cooling water must be given. So m dot C, we must determine the rate of cooling water. Okay, so first things first, the mass flux of R134A in the system is going to be fixed. So whatever R134 is coming in at, at this section is the same flux going out. There is no reduction in mass flux because it's a single pipe. Okay, it's gonna be a single pipe, and that is why there will be no change of mass. Similarly, whatever mass flux of water is coming in is going to be the same mass flux of water going out. Okay, now let us consider this as the control volume. Okay, for this particular control volume, we can now write down all the different conservation equations. So first, conservation of mass. Let me call this 1, let me call this 2, let me call this 3, let me call this 4. So m dot 1 plus m dot 3 minus m dot, oh sorry, m dot 1 minus m dot 2 minus m dot 3 minus m dot 4 is equal to dmcv dt, but this is a heat exchanger, it's a steady state steady flow process, so this becomes 0. So what do we have? We have m dot 1 plus m dot 2 is equal to m dot 3 plus m dot 4, but we have already seen, oh what have I done, this is all incorrect. Conservation of mass I have written down, let me write it down. So mass in will be m dot 1 and m dot 3. So m dot 1 plus m dot 3 minus mass going out is m dot 4 and m dot 2. M dot 4 plus m dot 2 is equal to dmcv dt, but because of steady state steady flow this will be 0. Therefore m dot 1 plus m dot 3 is equal to m dot 4 plus m dot 2. But we have already seen that because the pipeline of R134A internally is different from the pipeline of cooling water internally, m dot 1 will be equal to m dot 2, and similarly m dot 3 will be equal to m dot 4. So m dot 3, m dot 4, m dot 1, m dot 2 cancel out. So mass conservation is trivially satisfied. Mass conservation is trivial, no problem. Now with that in hand, we are in a position to write down the conservation of energy. Okay, so what was the conservation of energy? So ddt of ECV is equal to q dot to the control volume minus w dot by the control volume plus summation m dot I hi total minus summation m dot E he total. But because it's a steady state steady flow device, this vanishes. Moreover, a heat exchanger is an insulated device, meaning whatever heat is being transferred by R134A is solely to the water and it is not transferring any heat to the surrounding. Okay, so because it's insulated, the heat exchanger is insulated. This is an assumption. Okay, because it's insulated, there will be no heat fluxes to or from the system. Moreover, we are not extracting any amount of work from the heat exchanger, meaning there is no shaft work, nor is there any boundary work because the shape of the control volume also remains constant. So there is also no work done. In that case, we can write down this minus this equal to 0. So we have m dot I summation hi total is equal to summation m dot E he total. Now in this particular diagram, what does m dot I comprise of? The incoming mass flux comprises of this m dot 1 hi total, so h1 total plus what else is incoming? The cooling water plus m dot 3 h3 total is equal to exits. So the exits are m dot 4 h4 total plus m dot 2 h2 total. Okay, so this is what we have, and our original assumption that m dot 1 equal to m dot 2, m dot 3 is equal to m dot 4. So let's put that in action. So let's call this equation 1. Using equation 1, m dot 1 h1 total plus, rather we take this term on the left hand side, so minus m dot 2 h2 total is equal to m dot 4 h4 total minus m dot 3 h3 total. But because m dot 1 is equal to m dot 2, so this we can write down as m dot 1, and because m dot 3 is equal to m dot 4, this becomes m dot 3. So this is m dot 3 h4 total minus h3 total, and over here we have m dot 1 h1 total minus h2 total. So m dot 3 is the mass flux of the cooling water. So we can write m dot 3 is equal to m dot 1 h1 total minus h2 total divided by h4 total minus h3 total. Okay, so far we can write this. Let me just grab hold of this schematic because we are scrolling up and down way too much.
Sir, what we have to calculate M3 dot?
Yes, we have to calculate m3 dot.
Okay.
We have to determine the mass flux of the cooling water. Now, state 1 is R134A at 1 megapascal, 60 degrees Celsius. State 2 is R134A, 0.95 megapascal, 35 degrees Celsius. State 3 is liquid water at 10 degrees Celsius. State 4 is liquid water at 20 degrees Celsius. Okay, so with this, let us simply plug in the values. Let me open. So I'm doing it using ES. You are free to do whatever you want, but keep in mind whatever we have derived so far is the real deal. Everything else, is just you having to fetch values. I mean, I cannot emphasize this enough. All right, let me know if the screen is visible.
Yes, sir.
Yes, sir, visible.
All right, so okay, before that, H1 total, H1 total or any other total enthalpy is H1 plus half V square, velocity square plus Gz. We will assume in this problem, because the heat exchanger is small, there is no change in potential energy anywhere, and the flow rates are so slow that there is going to be no change in the kinetic energy, specific kinetic energy in the incoming system or the outgoing system. So the total energy coming in is solely because of the specific enthalpy, not because of specific kinetic energy or the specific potential energy. The specific kinetic energy and potential energy become important for a class of devices known as nozzles or diffusers. For many other problems, unless otherwise specified, you will simply neglect it. For example, in this problem, it was not at all given that the velocity has changed or this has happened. So in that case, you can safely assume that the kinetic energy changes are negligible. Okay, so all these total quantities are simply the specific enthalpy. So I will write down H1 is equal to enthalpy R134A, P equal to 1000 because it's 1 megapascal, T equal to 60. Then I will say H2 is enthalpy R134A, P equal to 950, T equal to 35. H3 is equal to enthalpy water T equal to 10, X equal to 0 because it's cooling water. H4 equal to enthalpy water T equal to 20, X equal to 0. So M3 will be M1 multiplied by H1 minus H2 divided by H4 minus H3, where M1 is given as 0.2 kg per second. Let me run this program. So M dot 3 comes as 0.9191 and the answer matches exactly with the textbook. Okay. So this is the mass flux of cooling water that you must have in order to cool R134A from 1 megapascal 60 degrees Celsius to points to 35 degrees Celsius. Now look over here. Ideally, heat exchangers are devices where the pressure drop is negligible. And the pressure drop is in fact negligible. The pressure drop for R134A, it goes from 1 megapascal to 0.95 megapascal. So what exactly is going on? You are essentially losing out on 50 kilopascal. Why is that? Who can tell why are we losing pressure 1 megapascal to 0.95 megapascal? You have essentially lost 50 kilopascal, which is not a lot. But why have we lost it? Anyone? Any
Viscosity.
guess? Huh?
Viscosity.
Yes, I mean it's due to the pressure losses because of the fluid flow within pipes. So essentially it's caused by viscosity. Okay, very good answer. So this kind of engineering sense one must have when defining. So the longer the pipeline you have, the larger the losses you will have. That is why you will see heat exchangers really, I mean, the designer has to account for that. He has to account for the fact that when the liquid comes out, it will be at a slightly lower pressure. Okay, so that's what you do with heat exchangers. Next, we have nozzle. So let me tell you what a nozzle is. A nozzle is a static device where it's simply a converging diverging section. So this is the converging section, this is the diverging section. And this kind of nozzle you will find in jet engines, in fact many other devices as well, but most prominently you might have seen it in photographs of jet engines. Okay, so what is the task of the nozzle? Like the task of the heat exchanger was to exchange heat between two fluids. One of the fluid could be air. What is the task of the nozzle? So the task of the nozzle is to create high velocity fluid stream at the exit at the cost of the incoming enthalpy. Whatever enthalpy is coming in, it will the whole task of the nozzle is to convert it into high kinetic energy. So as you can imagine, if the task of the device is to convert enthalpy into kinetic energy output, the output specific kinetic energy is something which we will not be able to neglect anymore. Moreover, this device is static. The incoming mass fluxes do not change. The outgoing mass fluxes also do not change. So a nozzle also falls under the classification of steady state, steady flow device. And a nozzle is typically insulated unless otherwise specified. Nozzle is insulated unless otherwise specified. There might be problems where you say that we have a non-ideal nozzle and there is some amount of heat transfer from the nozzle to the surrounding. In that case, you must be in a position to appropriately modify the first law of thermodynamics in order to account for that non-ideality. Let us consider this as the control volume. So, first things first, mass conservation. What about mass conservation? Is it ideal? Is it trivial? Yes, it is trivial. Why is it trivial? Because there is only one mass coming in, m dot I, let's call it, and this is m dot E. Okay, so m dot I simply is equal to m dot E because it's a steady state, steady flow process. Is that clear to everyone? It's the mass conservation is trivial for a nozzle.
Yes, sir.
Now let us write down the first law of thermodynamics. So we have dECV dt is equal to summation of all heat fluxes minus summation of all works plus summation of all inputs bringing in total enthalpies minus summation of all exit masses taking out all the total enthalpies. Because it's a steady state steady flow process, this vanishes. This vanishes. Why does this vanish?
Insulated.
The
Nozzle is
nozzle is
insulated.
insulated. This vanishes. Why?
Cross linking of control volume.
There is no boundary work, there is no shaft work. So essentially you are left with 0 is equal to this minus this. Alright. So much like the heat exchanger, summation m dot I hi total is equal to summation m dot E he total. This was the same case for the heat exchanger as well. But over here there is only one mass stream, so you will say m dot I hi total is equal to m dot E he total. But we have already seen that because there is only one inlet and exit, the mass conservation is identically valid. So m dot I and m dot E are equal, they cancel out, essentially leaving us with hi total is equal to he total. And this means that the incoming enthalpy is equal to the outgoing enthalpy total. Now what is the incoming enthalpy? It will be hi plus half vi square plus gzi, and the outgoing enthalpy will be he plus half ve square, so these v are the velocities, plus gze. Now because the change in potential energy in going from the inlet to the outlet is negligible, we can simply cancel these out. So these are cancelled because change in specific potential energy is 0. The change is 0. I'm not saying that the absolute value is 0. This nozzle could be at a very high altitude. Correspondingly, it can have a very high potential energy. But during the process, in going from the inlet to the outlet, the change that it experiences, that the fluid experiences, will be equal to 0. Therefore, we can cancel out these two terms. So we have hi plus half vi square is equal to he plus half ve square. That is the entirety of the derivation for a nozzle. Okay, this is what you will use for a nozzle. Let us do a small problem. The problem states the following. The problem states the following. Steam, so the incoming line, that this is inlet line and that is the outlet line. The incoming line has steam at 0.6 megapascal and 200 degrees Celsius, and it enters into an insulated nozzle. This nozzle is insulated. It is given in the problem. And it exits. No. So it enters the nozzle with a velocity of 50 meter per second. Okay, this is the incoming information. The outgoing information is 0.15 megapascal is the outlet pressure, and the velocity is 600 meter per second, which is two-thirds the speed of sound. The question is, determine the final temperature. It is given that the exit velocity and the exit pressure is this. The question is, what is the final temperature? If the steam is superheated, okay, so first of all, we have to find out the final temperature. The second part of the question we will come to later on. Okay, so hi plus half vi square. Okay, vi we have over here. So let's do that. A word of caution. This is the place where many of you might make a mistake. When using units, hi, the unit is what? Kilojoule per kg. Yes? Isn't it?
Yes, sir.
Now what is half vi square? What is v square? Unit of v square. It will be simply joule per kg. So in order to convert it from joule to kg, in order to have the same unit going around everywhere, you must divide everything by by a factor of 1000. Otherwise, you will be in a big soup. You will get all sorts of wrong answers. Okay, so in this case, for example, the kinetic energies, the specific kinetic energy will be half into 50 square over 1000. This is the specific kinetic energy. And the units of this now are kilojoule per kg. But if you only use, so this is half v square over 1000. If you only use half v square, you would have half into 50 square, and the unit of this would be joule over kg. So if you try to add something which is kilojoule over kg with joule per kg, you are going to get incorrect answers, solely because there's a factor of 1000 missing from either of the term. Either you can convert this to joule per kg, which is not so convenient because all the other quantities in the tables, they will be reported in kilojoule per kg. So it is worth your time to convert the specific kinetic energy head into kilojoule per kg rather than doing anything with the specific enthalpy units. Is that clear, everyone? It's simple, but I just thought it needs to be said. And most likely many of you might have figured it out as well. Is that clear?
Yes, sir.
So Hi plus half Vi square over 1000 is equal to He plus half Ve square over 1000. Okay, where Hi is at 0.6 megapascal, 200 degrees Celsius. This Vi is 50 meter per second. He I don't know. Ve is 600 meter per second. So let us plug in the numbers and let us see what He is. Okay, so I will say Hi plus half into Vi squared over 1000 is equal to He plus half into Ve squared over 1000, where Hi is the enthalpy of steam at T equal to 200, P equal to 600, and Vi is going to be 30 and Ve is going to be 600. So let us run this. So we get an exit enthalpy of 1051. So we have exit enthalpy 1051 kilojoule per kg. It is also given that the outlet state is at 0.15 megapascal. So the exit pressure is 0.15 megapascal. We have already
Okay.
seen in chapter 5 that enthalpy and pressure
Listen,
can be used for two independent quantities to determine the other properties. Yeah? Someone wants to ask something?
sir, I think you divided by 100 instead of 1000.
Ah, thanks for pointing it out. So let me just make amends over here.
Sir, also VI is 30 or 50?
Wasn't it 30? Oh, it was 50. My bad. I just change it. No problem. Thanks. So the exit enthalpy is 2672. Okay, let's write it down. 2672 kilojoule per kg. So good, at least you're attentive. You're more attentive than me. That's always a big plus. Okay, these are the exit quantities that we have. And like I said, we can use enthalpy and pressure to determine any other property that we want, like specific volume, temperature, internal energy, if one were to be inclined to find that. So now we will go ahead and find out the exit temperature. So T exit is going to be the enthalpy temperature of steam at H equal to 2672 and P equal to 150. Let me run this. So with this, we obtain an exit temperature of 111.3 degrees Celsius. Okay. So the final temperature is 111 point this, and okay, they have not told the correct answer, but the energy is correct. 2672 is correct. In the book,
So,
it is given as 2671. Yeah.
but in AES, my HE is coming different. My
The
HE is
offset.
coming out
So
2851.
no, check the difference. Check the difference.
Okay, sir.
Those
Sir,
off. Hmm?
sir, I have a doubt.
Hmm.
In this case, it is mentioned that, like it was steam. Like we know that its quality is one.
No, we don't know the quality is one. Nowhere have we assumed that the quality is one.
Okay, sir. I thought it was, and that's why I got an ambiguity.
No, no, there is no. We have never assumed it's never said it's superheated or subcooled or saturated. Let's see. I mean, if you have a doubt, let's see. Quality steam T equal to 200, P equal to 600. Let's see whether what state it is. So the incoming quality, I mean Xi is 100, meaning it is superheated steam. Okay. Hello.
Mm, hello, sir, but the outgoing is not matching. Like I thought, I checked at P equal to 150 and
Hmm.
X equal to 1. The HE comes out to be little bit different.
Let's see what the outgoing quality is. So the outgoing is 0.9905. So it's just at the saturation point.
Yes, sir.
One moment. Yeah, hello. Sorry about that. So the exit quality is very near to the saturation dome. And in the book also it is given as 0.99, which is correct. Okay, hello, Sayantan.
Yes, sir. Yes, sir. Clear. It is clear.
For everyone else, regardless of what value you get, it's just a matter of having what the internal offset of the software is. Don't worry about the absolute values ever. Hello?
Yes, sir.
Yes, sir.
To everyone, you should get 0.99. That's what I'm trying to say. Even if you use a table or whatever, you should not be flustered by this particular value of enthalpy that we have obtained. That should not concern you. But
So,
typically for Steam, EES and tables have the same offset. Yeah.
so what is the answer they are giving?
This answer that we have obtained. They have not found out the temperature, but because it's in the dome, it's in the dome. So what will be the temperature? It will simply be the temperature, saturation temperature at 150 kilopascal, won't it? And this is
Yes,
matching.
sir.
This answer is matching. Okay.
Yes, sir,
As
it's
per the
coming.
book, also it is matching. What is the doubt? This is a very straightforward problem.
No, sir.
I had put in some wrong values, which Sayantan I mean, what is it? Siley? Yeah, many people pointed out, but that's okay. But the answer does match with the book. In the book also, the exit enthalpy is given as 2671.4 kilojoule per kg, and that is as per the table. Okay. So if you were to do it using a table, how would you know that it's in the inside the saturated dome? We know that the exit pressure is 0.15 megapascal. Essentially, it is 150 kilopascal, and the
Sir,
enthalpy that
we
we get is, yeah,
sir, we will check enthalpy at 105 kilopascal and x equal to 1.
very good. So the enthalpy of vapor, is it the enthalpy at the exit, is it less than the enthalpy of vapor? If it is yes, then inside saturation dome, saturated dome. If the enthalpy at the exit is larger than this, then what does it mean, Shantam?
Sir, superheated.
Superheated. Very good. I mean, this logic you should always keep in mind when solving these problems, and then you will not make mistakes. So let us take a 5-minute break, after which we will cover throttling devices, we will cover turbines, and we will consider a slightly elaborate problem where all these instruments are joined in a big system. Okay, we will consider this, and lastly we will wrap up with a few transient problems. So buckle up for the second half.
Hello, sir.
Yeah.
Sir, in the exam, if it is asked about this question, will we start from the starting with the conservation of mass and everything, or we will directly
Yeah.
apply the formula?
I mean, see, to write that much, to just write that much, that conservation of mass is trivial, conservation of energy is this. It will take you no more than 10 seconds, right? Will it? Or do you really want to save
No,
up on that time? It will be very fast.
No, sir. I was just asking, sir.
No, no,
Here it is.
formula, don't use formula. I mean, when you just get it, it should strike in your head that yes, that is the correct form. See, in a non-ideal problem, I will say the nozzle is also losing heat. तब तो formula use करने से नहीं चलेगा ना. You get the point.
Yes, Avnish.
So might as well start with the basics. It just takes 10 seconds. Come on.
Yes, sir.
Okay.
Yes, sir.
So don't go anywhere. We'll be back with more problems.
Hello, sir.
Yeah.
Sir, I had a doubt not related to thermodynamics. Sir,
Oh,
how does this ES work? Like, it is not following the normal flow of code. So, like,
why not?
sir, in the previous problem, I said like you followed a pattern, but the value was calculated in the end, but the formula was used
Yeah, yeah.
before that.
So it compiles everything afterwards. It doesn't interpret line by line. It takes all the variables. It sees what all things it needs to solve. In fact, over here there is something even funny that it does, but it's very. Uh, so let me do this. I mean, it's just for fun. You should not do it because things may go wrong. You should not do all this, whatever I'm trying to show you. So h
Yes.
temp. So suppose h temp is 2672. Okay. Then I say h temp, or how can I do it? Mm, h temp equal to enthalpy of steam at T equal to T unknown, P equal to 150. Ideally, it should be able to solve this as well. No, 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 no. Oh, because I'm using see, where the error has come. T and P I'm trying to fetch to get enthalpy, but T and P cannot be used simultaneously inside the saturated dome. Inside the saturated dome, T and P cannot be used, so it throws an error. But had it been in superheated, so let me just put this, then it would give some answer. But the property is probably incorrect, so I need to go to a lower pressure maybe. No, it's still in the saturated dome. Anyway, if you can do such kinds of weird inverse equations and it still works. We don't, ideally you should never have to do that. Ideally you should never have to do that. You just do it in the normal logical way so that things don't go wrong. And you use ES as this property fetcher. What's wrong? You fetch properties, you write it here, you get it here. Use it as a elaborate calculator, as a steam table calculator if you want to call it. Is it clear to everyone what I'm trying to say? You use ES as a elaborate steam table calculator. Anil Maharia, is it clear what I said? He's not there. Devik Agrawal.
Yes, sir. So it's clear.
Anna. So fine. Take a 5-minute break. We'll be back. We have to cover more problems. Okay. So I'll see you later in 5 minutes. Okay, we're back. So then a diffuser. Okay. Uh, so a diffuser is a similar item where you have a converging section and a larger diverging section. It's the reverse of a nozzle. So diffuser is also insulated, and it makes use of the fact that high kinetic energy is coming in and you want to convert it into enthalpy. This kind of things you will also see in jet turbines, but the analysis remains the same. Okay, so the next thing. So we'll not discuss problems of this. It's very simple. It's the same idea as before. So throttling. Throttling is a very common process in air conditioners or refrigerators. Okay, and it's very simple in the sense that it's nothing but in the tube you will have a small orifice. This is the orifice. Okay, and if we imagine this to be the control volume, if you imagine this to be the control volume, the process of throttling happens so fast that there is no chance for the refrigerant, which is entering at a certain enthalpy, to lose heat to the surroundings. Okay, and the throttle valve is also packed with thermocol, so it's insulated. So throttle is insulated also, and during this process the upstream velocity, so look at this, I have not drawn the control volume very close to the orifice, I have drawn it far. So very close to the control surface and rather away from the orifice, at the inlet control surface, inlet, and at the outlet, the velocities are the same. Why are the velocities same? Because the mass flux is still maintained. Okay, so when the velocities are same, rather, let me put it this way, the difference in specific kinetic energies is negligible. In that case, the enthalpies will remain constant. Let's derive this. So mass conservation. What is mass conservation again? Is it trivial or not? Only one inlet, only one exit. Is mass conservation
Yes, sir.
trivial?
It is trivial.
Yes, sir.
It is trivial. And it's also a steady state, steady flow device. Okay, so we have dECV dt is equal to q dot summation minus summation of w dot plus summation m dot I hi total minus summation m dot e he total. So there is no heat transfer, there is no work done. It's a steady state, steady flow device. So again, you end up with the same formula. So m dot I hi total is equal to m dot e he total. So let us write down the expression for this, and mi and me they cancel out because from mass conservation we would have m dot I is equal to m dot e. So by virtue of this, these two terms cancel out. So hi total will comprise of hi plus half vi square plus gzi, and he total will comprise of he plus half ve square plus gzd. Now there is no change in specific potential energy and there is no change in specific kinetic energy. So these terms cancel out. They are not negligible, they cancel out, meaning the change is zero. Okay, I have not cancelled them individually, I have cancelled them in pairs because half vi square will be approximately equal to half ve square. Okay, there is a difference. I hope everyone is able to understand that. I am not saying half vi square is equal to 0. I am saying half vi square is approximately equal to half ve square. That is why I have cancelled them out. So finally, for a throttling process, you have hi equal to he. So a throttling process is therefore known as an isenthalpic process. Okay, is it clear? Hello?
Yes, sir.
Yes, sir.
It's very simple. So with that in mind, let's do a simple problem. So we have a capillary tube throttling device. So it's also called as an expansion valve, and in refrigerators it's also called as a capillary tube. Basically it has a very small diameter, so it's an expansion valve or a capillary tube as well. So what is given? In this you have ammonia as the refrigerant, which enters the expansion valve at 1.5 megapascal and 35 degrees Celsius, and it exits the expansion valve at 291 kilopascal. The question is, what is the quality of ammonia going out? So let's see how we can do it. It's very simple. So we will say HI, that is the incoming enthalpy, is the enthalpy of ammonia at T equal to 35 and at P equal to 1500. We will say HE equal to HI because the exit enthalpy is equal to the incoming enthalpy. And finally, X exit is the quality of ammonia at H equal to exit enthalpy and P equal to 291 kilopascal. So when we run this, we obtain a quality of 0.1636. So the quality unknown is 0.1636, and the answer given in the textbook is 16.38%, which is fine. Fourth decimal place we have some difference. Okay, the problems of expansion valves are as simple as that. They are isenthalpic processes. That is, the enthalpy upstream and downstream, they remain the same. Any doubt in this so far?
No, sir.
So I have a doubt in the concept. So that orifice is very small, but still velocity is remaining unchanged. So how
Yes.
it is? I'm not understanding.
No, so this velocity, the design of the capillary valve or the expansion valve, it is done in such a way that the velocity remains constant. You don't want large changes in velocity in the system. In a refrigeration system, you design everything in such a way that the velocity tends to remain constant. Otherwise, you will have all sorts of fluid pressure drops. Difference in velocities cause drops in pressure. So during the designing of the process, it is always ensured that the inlet incoming and outgoing velocities are same. I'm drawing it as a very simple orifice, but in reality it's a coil of capillary. The length and the diameter are chosen appropriately so that the velocities remain same. Okay.
Okay, sir. And so one more doubt. And so you told that heat exchange is also like negligible.
Hmm.
So like are they using any material or what?
So typically the heat exchange will be very small because the process happens in a very small area and it happens very fast. The second thing is it's also covered with an insulating cover. These two factors make it
Okay, sir.
practically insulated. Okay.
Yes, sir.
All right. So let's proceed. Let's proceed to finally do turbines. Okay, turbines are expansion devices where something comes in, there's a shaft, there's a series of blades, there's a series of rotating blades. Actually, the design is very complicated. It's not just like series of blades and the shaft, but for this particular course, we can imagine it to be something like this. And when high pressure, high temperature working fluid comes in, eventually it goes out as low temperature, low pressure working fluid. This is high temperature, high pressure. So in going from high temperature to low temperature and in going from high pressure to low pressure, whatever the loss of enthalpy is converted into shaft work. And it is also mostly the case that the turbine may be assumed to be insulated as well. In many cases, it will be given that the turbine is insulated, meaning there is a layer of insulation so that it doesn't lose heat. Why do you want the turbine to not lose heat? Because losing heat meaning whatever output you could have obtained, part of it is converted to heat and lost to the surroundings. So the potential work done that you can get, that will get reduced. So in order to avoid that, it is also kept insulated. It's a kind of rotary device, and yeah, typically you have high temperature high pressure coming in and low temperature low pressure going out. This is what the entire situation is. So the questions will be, what is the work output of a turbine, for example? And apart from having high temperature high pressure, it also will be high velocity. High velocity, here it will be low velocity. Okay, so let's do a problem. It will become very clear through the problem what the entire analysis of a turbine looks like. Okay, that's a very poorly drawn turbine. Okay, yeah, this is a good turbine. This is the output shaft. So the incoming, let me draw it in magenta. So it is given that for this turbine, the mass flow rate is 1.5 kg per second of steam. Steam. It is given that the incoming pressure is 2 megapascal. It is given that the incoming temperature is 350 degrees Celsius. It is given that the incoming velocity is 50 meter per second, and also it is given that the potential energy or the height is at 6 meters. So this is Zi. This is Vi, temperature, pressure, mass flux. At the exit, the state is given as, so what is mass conservation in this case? Is it trivial or not? Mass conservation in this case, is mass conservation trivial?
Yes, I think because there is a one inlet and one outlet.
Very good. So there is only one inlet, one outlet. So the mass exit will also be 1.5 kg per second. It is given that the exit pressure is 0.1 megapascal, which is almost atmospheric pressure. The exit quality is given as 100%, meaning that the exit is at saturated vapor. The exit is at saturated vapor. Then the exit velocity is 100 meter per second, and the potential, the height change is 3 meters. This is all that has been given. So then the question is, what is the work output? But in this particular problem, it is given that there is certain amount of energy loss, a certain amount of heat loss, and that amount of heat loss is 8.5 kilowatt. Okay, the amount of heat lost is also given. So heat lost by the system is positive or negative? It is negative.
Negative.
So this we have to account for in the first law of thermodynamics. Okay, so let me just grab hold of this and put it to the side so that we can do the analysis over here. So mass conservation, that is trivial. Energy, dCV dt is equal to sum of all heat fluxes minus sum of all works plus summation m dot I hi total minus summation of me he total. Okay, because it's a steady state device, this vanishes, and we can finally write q dot is equal to, or rather q dot plus m dot I hi total is equal to w dot plus m dot he total. Now let us find out each of the terms. So first of all, let us write down q dot. So it is minus 8.5. Okay, this one we know from the problem. What is hi total? It is going to be hi plus half Vi square plus Gzi. But over here, again, I am repeating this, and please do not make this mistake. When you want to use Hi as kilojoule per kg, you must divide this by 1000. You must divide this by 1000. Okay? Will you remember to not make this mistake? If you simply use GZI, the unit will be joule per kg. If you simply use half Vi square, the unit will be joule per kg. So in order to make it kilojoule per kg, you divide it by 1000. And in order to make this kilojoule per kg, you divide it by 1000. Okay? Remember this. So what is Hi total? Let's see. Let's find it out. Ideally, you would not calculate each of the terms. So let us find out only Hi. It is the enthalpy of steam at P equal to 2000, T equal to 350. Let's find it out. So Hi is 3138. Let's find out what half Vi square is. So KEI, that is the kinetic energy at specific kinetic energy at the inlet. So this is half into Vi square, which is 50 squared divided by 1000. So when we run this, what do we observe? The kinetic energy incoming is very small. It is very small compared to the enthalpy. Are you able to appreciate this fact?
Yes, sir.
Moreover, the potential energy at the inlet is going to be 9.81. If I consider this height to be from some absolute value which is at z equal to 0, so it will be times 6 over 1000. So the potential energy contribution is even smaller. That is why we say that for the inlet to the turbine, the most dominant contribution is through the enthalpy only. Okay, the dominant contribution is mostly through the enthalpy. Okay, regardless, so Hi total is equal to Hi plus kinetic energy I at PEI. Now, what is the exit condition? He is equal to enthalpy of steam at P equal to 100, X equal to 1. Kinetic energy at the exit is the half into 100 square divided by 1000. Potential energy at the exit will be 9.81 into 3 divided by 1000. So HET, that is the total enthalpy at the exit, which will be He plus kinetic energy at the exit plus potential energy at the exit. So when we run this, we get certain values, no problem. Okay, so far what have we calculated? We have minus 8.5 kilowatt plus, so the mass flux is given as 1.5 plus 1.5 times Hi total is equal to W dot plus 1.5 times He total. So the work output will be minus 8.5 plus 1.5 into Hi total minus 1.5 into He total. Or rearranging this, I can write this as minus 8.5 plus 1.5 Hi total minus He total. So let's see what that is. So let me call this term 1. So just to show you what the relative orders of magnitudes are. So term 1 will be 1.5 times Hi total minus He total. Let me run it. So term 1 is 688.4. So this becomes 8 minus 8.5 plus 688.4 kilowatt. Okay, let me just tell you how it is kilowatt. So 1.5 kg per second multiplied by, so this specific quantity will be kilojoule per kg. So kg cancels out. So you get kilojoule per second, which is kilowatt. That is why this entire unit is in kilowatt. This should have been clear by now. So what is the total work output? So the work output is minus 8.5 kilowatt plus this T1. So the final work output is 679.9 kilowatt. So this turbine gives you a work output of 679.9 kilowatt. The answer given in the book when you do it using tables is 678.2 kilowatt. Is that okay?
Yes, sir.
So what are the observations that we make in the problem? The observations are the heat transfer is also quite negligible compared to the actual work output. Okay, compare this. This is the work output. The heat transfer is only 8.5. What is the fraction? It's very small. Okay, it's very small. So heat transfer, that is why heat transfer in most of the cases is neglected. Moreover, we have also seen that the specific internal energy and specific potential energy are also negligible as compared to the enthalpies. And that is why they can also be usually neglected. But in a problem, if the information is given, you might as well put in all the information and not skip any step. Is it clear?
Yes, sir.
Aryan Burdia, is it clear? Bhavya Sharma, Manoj,
Yes, sir, it's clear.
Yes, sir.
Chetan, Manoj Raj is not there. Nandini, Harsh was the first person to join the class. Harsh, is it clear? Okay. Niranjan,
Yes, sir, clear, sir.
very good. Minal, Rahul Gupta, Rajdeep Das, Shrutika
Yes, sir.
Patel. Yeah, is it clear, the analysis?
Yes, yes, yes.
Okay. Shrutika, Soumyaranjan Sahu, Spandan Mitra, Swasti Singh. Tushar Punia is definitely
Yes,
there.
sir.
Yes,
Okay,
sir.
very good. Yeah. Vashu. Yogendar Arya is on hold. I don't even know what that means. Yogendar Arya is on hold. Meaning he is on a phone call, is it?
So
Yogendar?
phone call or different meeting.
Or a different meeting. Okay. Wow. Anyway, what can I do? I cannot grab you by the ears and make you do this class. Okay, let's proceed. Let's proceed. Okay, so whatever I just did for a turbine, the reverse is true for a what do you call it? For a compressor. So a compressor is a similar device. It's I mean fundamentally speaking, it's the opposite of a turbine. Okay, so it's not really worth our time to discuss how a compressor analysis is done. It's exactly the same as above. Compressor, it takes in stuff at low pressure, low temperature, and out. So low P, low T, and the output is high P, high T. Okay, but the analysis is going to be the same. The analysis is going to be the same. And finally, we come to a slightly complicated problem. Oh no, the problem we will do at night. The problem we will do at night. If anyone interested can look at the recording. We will now cover the last part of chapter 6, that is the transient process. Transient process. So whatever we have studied so far, that falls under the classification of steady state, steady flow device, right? And you may think that there could be many processes where it's not steady state steady flow, and it is true, but the number of devices which operate as a steady state steady flow device, it is very large, and that is why all the previous analysis are very important. But a transient process is also very legitimate. For example, in a oxygen's filling plant, you have these bottles. I mean, this is a very poorly drawn bottle, and you want to charge it with oxygen. You know, the tank becomes empty and there is a small valve, so you connect it to a pipeline. That pipeline is containing oxygen, and this pipeline continuously, air is coming in, oxygen is coming in, oxygen is going out. When you open this valve, then this tank, which originally has no oxygen, it will get filled with oxygen, and then you close the tank. So this kind of process where you have state 1, no oxygen in tank, then intermediate step, the valve is open, then step 2, O2 is filled in tank, then final step, valve is closed. For such kinds of processes, one must undertake a transient analysis. Okay, so let us first look at the derivation of a transient analysis. It's the starting block is the first law for a control volume, and then we will do certain things, and it should be obvious what we're going to do. We will integrate it in time. So first of all, mass conservation. First things first is mass conservation. So dmcv dt is equal to summation of m dot I minus summation of m dot E. Okay, this is the conservation of mass. Let us integrate this in time. Integrate in time. So what do we have? Integral dmcv dt is equal to integral summation m dot I dt minus integral summation of m dot E dt. So what does this become in going from state 1 to state 2? So in going from state 1 to state 2, it will simply be mcv at some time 2 minus mcv at some time 1. Okay, and when you integrate the mass flux over time, you will simply get summation m dot I minus summation not m dot I minus summation me, meaning you have taken whatever the mass flux is, you have integrated in time. But if you imagine that over that time, in going from point 1 to point 2, in going from time 1 to time 2, during that time, if the mass flux is constant, then this will be m dot I multiplied by delta t, and this is simply all the mass that has come into the system. I don't know why I'm drawing this dot. This will be all the mass that has come into the system. Okay, this is important. Even if you don't assume that m dot I is constant, this will be equal to some average mass that has come into the system. Okay, so change of mass in the control volume will be equal to all mass transferred to the control volume minus all mass taken away from the control volume. Is that okay, guys? If you have any doubt, you ask. I can explain this again if you like. Let me pictorially draw it, then it will be clear. Suppose in time, I am looking at the inlet mass flux. So suppose it is constant. This is m dot I. So what is the total amount of mass that has come in? It is integral m dot I dt in going from time 1 to time 2. So it will be the area under this curve, and it will be simply m dot I multiplied by T2 minus T1, that is delta T, and this will be simply, I will call it Mi, all the mass that has come in to the system. Now alternately, I can say that during the process m dot I can fall, m dot I can go like this. Okay, it can fall, no problem. So this is how m dot I varies in time. These problems are significantly more complicated. So typically what you say is integral m dot I dt. Here you cannot simply write it as m dot I into delta t. Why can you not write this? Anyone? Why can you not write this for this red curve?
So because it's not parallel to x-axis.
Yes.
Yes, because it's a function of time and we cannot simply perform the integration. But I can simply say it is equal to m dot I sum average times delta t. Meaning I am effectively taking the average of this m dot I, say this is that. So this is m dot I average, and then I multiply by delta t, and effectively I got mi. So this is the area under this curve now. Okay, and that is all the mass that has come into the control volume. It's nothing more than this. It's just all the mass that has come into the control volume. Okay, so essentially the statement still holds that this is the rate of change of mass in the, not the rate of change of mass, this is the change of mass in the control volume, and the change of mass in the control volume has been affected by all the masses that have come into the control volume minus all the masses that have exited. There is no rate anymore. Okay, now is it clear to everyone?
Sir,
Yeah.
sir, actually I don't think that averaging is required, because like dmcd by dt into dt will simplify to dmcd, so it will be simply m1 minus m2, m2 minus m1.
That is true. What you said is true. But what I was deriving is for this particular fellow. This and this.
Okay, sir.
Okay, this is true. This is, I mean, this is straightforward. There is nothing to do in this. These are the incoming mass fluxes integrated over time. Okay, this analysis is for integrating fluxes over time. Is that clear?
Yes, sir.
It's not the first term. It's the second term. Okay. Now we move on to the conservation of energy. And it's going to be the similar thing. So we have dECV dt is equal to summation of q dots minus summation of w dots plus summation of mi hi total, m dot I hi total minus summation of m dot e he total. Now you integrate it in time. So what you get from the first term dECV dt integral dt is, it will be ECV2 minus ECV1. Okay, when you integrate the second term integral q dot dt, summation of q dot dt, it will be simply all the summation of q's. Meaning in going from time 1 to time 2, all the heats that have been transferred, that is being accounted over here. It's the same logic as before. It's the same logic as before. Third term, summation of w dot integral dt, it will be all the works that have been output in going from time 1 to time 2. Similarly, summation m dot I hit dt, it will be simply summation m dot I, not m dot I, summation mi hit. When is this valid? Now you should be able to tell me, if you've understood that integration before, if you have understood everything like this, you should be in a position to tell me when is this valid. let me remove the summation. So summation is for multiple mass fluxes. If we consider only one mass flux, so say integral m dot I hi total dt. When will it be able to? When will it be equal to m dot mi into hi total? When will this true?
So when HI will not be varying so much, or HI is like average.
Yes, sir.
Very good, very good. So this result is true when mi dot and hi t are not changing in time. Okay, this is true when mi dot and hi total are not changing in time. Okay, that is the correct answer.
So
Otherwise,
why should mi dot remain constant?
it does not have to remain constant. But in the processes, we will assume that it will remain constant unless otherwise specified. You can have a process where mi is not constant. Mi dot is not constant. In fact, when you try to fill air into your bicycle tire with the help of a pump, okay, initially there is no sort of no air in the tire, so initial mi dot will be higher than what the mi will be when the tire is partially full. Okay.
Sir, initially will be higher.
Huh? This is
So
the control volume. Yeah, tell.
sir, initially it will be higher, I guess.
Yeah, initially it will be higher, then it will fall. So in time, mi dot is going to vary like this. No?
Yes, sir.
Yes, sir.
Then nothing else. This integration will only become complicated. So I must also tell you how mi dot is varying in time. Otherwise, I will not be in a position to do this integral at all. I will not be able to do this integral at all. Moreover, hi total that is incoming, that is this line that connects the tire, the air that is going in, this condition is the hi total. No, guys?
Yes, sir.
Yes,
So
sir.
now there is no guarantee this will also remain constant, because when you are pumping air, this tube slightly becomes hot. So hi total will also slightly increase.
Even the pressure will also
Sir, yes,
change.
sir.
So back pressure
Pressure.
also changing. So a lot of things are changing. That is why we say that in this analysis, unless otherwise specified, m dot I HIT you will approximate as mi HIT. If they give you how it varies, then you can perform this integration. Try to understand. I'm not saying this is impossible to perform, but I must give you that information.
So but then like we can write mi dot as dmi by dt. So
No, you cannot write it as dmi dt
why so?
because it's a flux. It is not rate of change of some mass. It is the mass flux. It is the rate of mass coming in. You should not interpret it as dm dt. If
So
you
what's the
want to
difference between two?
see, I mean, there are the subtleties. M dot. So m dot is the it denotes the flux. It is because of some mass crossing a cross section. dm dt that we have used so far, it is the rate of change of mass in a fixed volume. Mathematically speaking, m dot you can write as dt. So you can say dm dt. This is what you want to say, right? Then you say is m cancel. No, it doesn't work that way. Why it doesn't work that way is also obvious. M dot is not a fixed mass, so when you do m dot dt, it is as if you're trying to sit over here and figure out how much mass has crossed this area. Now, if m dot is fixed, no problem. If m dot is a function of time, as we have discussed over here, you have to appropriately put that function of time and then integrate this. dm dt can also be a function of time, but why would you do that? Okay, I can say that initially m dot, so I can say that there is a process where the mass flux in the system decreases hyperbolically, meaning m dot is some constant over time plus some other constant, so that t equal to 0 doesn't become singular. I can say something like this. So then in going from time 1 to time 2, what is the total mass? Integral m dot dt in going from time 1 to time 2. So this will be a over t plus b dt, and this will be equal to what? A log t2 plus b over t1 plus b. No?
Yes, sir.
So this is that integration. So you cannot say this is dm dt. But when you analyze the control volume mass, it's already in this dmcv dt form. It doesn't matter how the process looks like. This particular integration for the mass flux, it depends on how the process looks like. Depends on path taken. It's a path integral. From mathematics, it's a path integral. But so it's an imperfect integral. From mathematics, if you recall, it's an imperfect integral, this. But this is a perfect integral. dmcv dt dt, it's a perfect integral. It does not depend on the path taken. Is it clear what I said? This is a
Okay.
perfect integral. You look at it from a holistic viewpoint. Don't try to recall from memory. Okay, so this then also boils down to, so let me just grab hold of this. When you integrate this, eventually you get ECV2 minus ECV1 is sum of all the heat transfers to the system minus sum of all work done by the system plus, so this will be approximately MI HI total. This will be approximately all ME HE total. Let's do a quick problem so that there is no doubt in anyone's head. Very standard problem. Very standard problem. Okay, so there is a valve and it is given that in this pipeline steam flows at 1.4 megapascal and 300 degrees Celsius. Steam is flowing in a pipe. So this pipe is a part of a big pipeline, but always steam will be flowing at 1.4 megapascal 300 degrees Celsius. It's like a big plant where steam is generated. So small cylinders like this, when you fill, it will not create any changes in the pipeline. Have I made myself clear?
Yes, sir.
So
Yes,
what
sir.
is the ramification of this statement? The ramification of this statement is this particular state will not be affected anymore, and so HI will not change. HI will never change. Okay? If I were to connect steam from a container to another container, then HI would change. I will discuss this later. Okay, so let's draw the control volume. This is the control volume. So what is the problem? So the valve is opened. So this tank is initially evacuated. There is nothing in the tank. And finally, when the valve is open, the final state is steam exists at 1.4 megapascal. This is all that is given. When the valve is open, this steam will go from the pipeline to the tank, and the pressure will reach 1.4 megapascal. It is also given that the process of filling process is adiabatic, meaning there is no heat transfer. and the kinetic energy and potential energies are negligible. So how do you solve this problem? First things first. First things first.
Sir, what is asked? What do you have to calculate?
We have to calculate the final mass of steam. No, final temperature of steam. We have to find the final temperature of steam.
Okay.
Now you might be tempted to say that it's going to be 300 degrees Celsius, but it's not. You might be tempted to think that it's going to be 300 degrees Celsius because it's connected to the pipeline, but no. It's a closed chamber, it's an open system. Here steam is constantly flowing. So first things first, conservation of mass. You always take it step by step. mCv2 minus mCv1 is equal to all the incoming mass minus all the outgoing mass for this red control volume. What is the initial mass in the control volume?
0.
0.
Zero.
It is 0. It is 0. So mCv1 is 0. Is there some mass coming into the control volume?
Yes, sir.
When the valve is open, this term will exist. Is there some mass exiting the control volume?
No, sir.
No, sir.
This will be 0. So conservation of mass gives us that mCv2 is mi. So whatever mass is coming in through the pipeline over here, so this is the inlet condition. Whatever mass is coming in through this point, right? It is going to be responsible for the mass collected in the control volume. Okay? Mass that has crossed the valve is responsible. This is responsible for final mass in the control volume. Okay, is this clear? This is very straightforward. Hello?
Yes, sir. Sure.
So let me just put it over here. So conservation of mass is trivial. Very good. Second step, conservation of energy. Or in first law, basically, first law. So you have ECV2 minus ECV1 is equal to all the heat transfers to the system minus all the works done by the system plus m dot, not m dot. This is m hi total, mi hi total minus me he total. Is there any work done? No, there is no boundary work, there is no shaft work. Is there any heat transfer? No, because the process is adiabatic. Is there any exit mass? No, Me is 0. Was there anything inside the control volume initially? No,
No,
it was
sir.
evacuated. So we have ECV2 is equal to Mi Hi total, and ECV2 is equal to mCv2 times ECV2. So ECV2 is equal to U plus half VCV square plus half GZCV, and HI total is HI plus half VI square plus GZI. But in the problem it is given that neglect the kinetic energy and potential energies. So neglect all this. Neglect all this. Finally, what do we get? From this expression equal to this expression, and we have mCv2 times U2 is equal to Mi Hi. But from mass conservation, what had we obtained? From mass conservation,
mCv2 equal to mi.
mCv2 equal to Mi, no problem. So mCv2 is equal to Mi, they cancel out. So U2 is equal to Hi. Now what is Hi going to be? Let me write this same formula above. So U2 is equal to Hi. What is Hi? How do you figure out what Hi is? Hi is the incoming enthalpy into the system. This is the incoming enthalpy coming into the control volume. So what is the incoming state? What is the incoming state?
Same as the stream of 1.4 megapascal and 300 degrees Celsius.
So it is steam at 1.4 megapascal, 300 degrees Celsius. So now I know that U2 will be something, it will be corresponding to HI, and I know that the final pressure is 1.4 megapascal. Okay, I have two state points known, so then I should be in a position to figure out what the final temperature is. So I will say that HI is equal to enthalpy of steam at what was it? 300 degrees Celsius,
300.
and P equal to 1400, and this is going to be U2. Okay, so this is the internal energy of the system when the valve is closed. Okay, after letting it fill. But I know what P2 is. P2 is 1400. Then I can simply fetch what is T2. Temperature, steam, P equal to P2, U equal to U. And the final temperature is 452.3 degrees Celsius. Okay, so T2 comes out to be 452.3 degrees Celsius. So what does that mean? After the filling process, when you fill the tank from a pipeline, so pipeline temperature is 300 degrees Celsius, but due to filling in a constrained volume, due to filling from a pipeline into a constrained volume, the temperature actually increases. And if you are a very observant person, you will see that when you fill air into your bicycle tire also, this is going to your bicycle tire, the tire becomes warm slightly because you are filling air into a closed volume. You are pushing more and more air into a closed volume, so the temperature increases. Okay, this is a very important class of problems. This kind of analysis is very true for many industrial processes as well. But am I able to convince you that these problems are not difficult? Rather, they're rather straightforward. There's nothing much going on. You must clearly identify what is the mass coming in, what is the mass going out, what is the energy coming in, what is the energy already there. Okay, so tonight we will discuss more problems on this. Please try to attend tonight's class for your own benefit. I'm saying tonight we will discuss many important classes of problems which might be useful to you in your future.
Hello, sir.